Assalamu alaikum warahmatullahi wabarakatuh. In this particular lecture series, I will be teaching you the topics related to renewable energy course. So, two main technologies will be covered in this course. The first one is the photovoltaic technology, and the second one shall be the wind power systems. So, in today's class, I will start discussing the PV materials and characteristics. In this context, we will understand what are the common materials which are used in designing a PV solar cell, what are the properties of these different materials, and how they correlate with the solar spectrum on this planet Earth. We shall now start with the historical background of the photovoltaic system. It all started in 1839, that discovery by a French scientist, Edmond Becquerel. So 1839, it is the discovery of the PV effect. Then in 1876, the photovoltaic effect on solid material was studied by Adams and Day, and that was only providing able to that was only able to provide 1 to 2% efficiency at that time. So this one was by Adams and Day, and the difference between the pioneering work by Edmund Becquerel and this work produced by Adams and Day was the impact of or the PV effect on solid material. Then in 1904, the most famous scientist known, Albert Einstein, he theoretically explained the PV effect. Against that discovery, he was awarded the Nobel Prize some years later in 1923. So in 1904, this Albert Einstein, he was able to theoretically explain the PV effect. Thereafter, in 1920s to 1930s, Chokralski developed methods to grow perfect crystals of silicon. So it was more into the material aspect, that crystallization of silicon was developed in a process which was introduced by Chokralski. And thereafter, it was a silent period for the PV technologies until in 1958. Solar cells were used in the satellites, which were, for example, the Vanguard satellite one. Solar cell was used in this particular satellite. And thereafter, the use of solar cell was limited to the satellite technology, until the world saw the oil embargo problem. Thereafter, the West, specifically the USA and their associated allies, they started to go for the commercial production of the photovoltaic panels. So in 1980s, the production of commercially available PV cell or PV modules were started. Then thereafter, from 1980s to the 21st century, there were hurdles related to the cost of the of the photovoltaic panel, and because it's always difficult to break the inertia of a society to introduce new technologies, it took some time. By the 2000s, we have only 600 megawatt of worldwide production. But thereafter, in the last decade specifically, large photovoltaic power plants were installed in various countries, which were led by the Germany, then China, and we have seen tremendous amount of photovoltaic power plants installed in Pakistan, India, as well as in USA and other countries. So it was a rapid, increase in the electricity production worldwide, and till in 2022, the things are have surpassed over 150 gigawatt of solar PV production across the globe. So what is actually a PV material? PV photovoltaic use semiconductor devices to convert, or semiconductor material to convert the sunlight into electricity. So if we talk about the solar PV, we require to have semiconductors to convert the sunlight into electricity. And for this thing, like all the other semiconductor devices that we used to study, a pure crystalline silicon is the starting point. So the starting point is the silicon, which is denoted by Si, and it has an atomic weight equals to 14. But the the placement of electron is such that we have two electrons in the innermost shell, then we have 8 electrons in the middle shell, and in the valence shell we have 4 electrons. And therefore, based on this number of electrons, which are 4, which are present in the valence shell, this silicon is uh, classified as a tetravalent, material or element. Silicon is a very interesting material. At T equal to 0, it is a perfect insulator. And as we increase the temperature, electrons, they get excited because of the energy which is available to them because of the increase in the temperature, and they manage to escape themselves or free themselves from the nucleus, from the power which is exerted on them from the nucleus. So as we increase the temperature, their conductivity G actually increases. But even then, if even if we increase the temperature is increased, we do know that the more number of electrons are available in the conduction band, and therefore we say that the conductivity of the silicon increases. Doping is used to enhance the conductivity of a pure silicon material, and that we have studied in detail in at our first course on electronic devices and circuits. Here, what I would like to introduce is the concept of or the treatment of silicon in terms of the quantum theory. The quantum theory states that the energy band diagrams are used to differentiate the metals and the semiconductors. So, for instance, we have a connection band here. Let us say this is the connection band. In between two bands, there are the forbidden bands that exist, and an electron is required to cross these forbidden band to in order to go into the connection band. So, for example, we say that this is a conduction band. This is the conduction band here, and this is a forbidden band. Then we have the filled band, where we have the electrons which are placed in these filled bands, and then we have the gap, and again then we have the filled band. As we increase the electron energy, the conduction band or the status of the electron actually changes. So what the concept here is in terms of this quantum theory is that based on the energies, the electrons are placed inside certain allowable energy bands which are shown here. For example, this one is one such band where we have some electrons placed on based on their energy levels. Then we have another band here. This is also based on some energy level. Then we have a forbidden band, and in conduction band, for if we talk about a metals, it is mostly partially filled, or we can say that it is half filled, because in conductors we do have some electrons which are available in the conduction band. So this is the topmost band, and it is that band where the electrons which are present in this conduction band, they are actually the contributors in the electron flow. So as you can see here, if I say that this one is a metal, and this is the quantum theory based energy band diagram of a metal, you can see here that the conduction band is already half filled or partially filled. Whereas if I draw the same diagram for a semiconductor, so in semiconductor, the conduction band is entirely empty at T equal to 0. For instance, if I'm talking about a silicon, then we have this entirely empty, this conduction band at this T equal to 0 Kelvin. This is entirely empty. Thereafter, we have some Eg, which is the forbidden band. We have some forbidden band here. And then we have the filled band. Then we have the gap, and then we have another filled band. So we do have the electrons present based on their energy values. They are present in these filled bands. But the conduction band is entirely empty as far as the silicon is concerned at T equal to 0 Kelvin. So if we increase this temperature a little bit and we try to quantify this particular thing, even at T equal to 25 degrees centigrade, 1 out of 10 raised to the power 10 electrons in silicon actually exist in this particular conduction band. So now what we have understood from this particular quantum energy band diagram, that there is a filled band and a conduction band, and the conduction band is that particular band where the presence of electron contributes towards the flow of current, and filled band are those band where we have placed the electrons based on whatever energy level they have. Higher the energy level they have, the more they will move upwards, which means that electrons must gain energy to jump over these gaps or this forbidden band to move to the next band. And the energy which is required for an electron to promote itself from this filled band into some other band of higher level, they require some energy which is known as a band gap energy, right? So I can say that this band gap energy is required for electron to move upwards. And this band gap energy is known as the Eg. It is known as Eg, and this E sub G has a units in EV, which is the electron volts, right? And this 1 electron volt is equal to 1.6 times 10 raised to the power minus 19 joule. And this band gap energy is dependent on the material which is used to construct or which is used to in making a semiconductor solar cell. So the band gap energy for silicon, because we are discussing about this silicon here, this band gap energy for silicon, if I say that for silicon, the band gap energy requirement is 1.12 electron volt. This indicates that if we have this silicon material available, an electron want to jump from this field band into the conduction band, it has to have 1.12 electron volt band gap energy to free itself from the electrostatic force and consequently jump into the conduction band and contribute for the towards the electric current. Now the question is that from where the electron will be able to get this much amount of the threshold energy 1.12. So there are two important sources, could be important sources of this band gap energy for the silicon, and one is we can get this from some thermal excitation. So we have change in temperature, the electron excite, it gets some energy. So this energy will be able to promote or to relocate the electron from a filled band into the conduction band. In PV sources, this energy Eg comes from the photon which is coming from the sun. So whenever a photon with more than 1.12 electron volt of energy is absorbed by a solar cell, it actually knocks out a single electron from this filled band into the conduction band. So consequently making an atom becomes positively charged, just like this one. So for example, we have this +4, this is the atomic weight of the silicon. Here we have the structure of a silicon. So suppose that we have some photon, it knocks on to this material. So what happened here is that it makes one of the electron free from this structure, and consequently it becomes a free electron and thereby creating a hole here. So the point here is that the photons, if the photons have energy greater than 1 point or equal to 1.12 electron volt, whole electron pairs are created, and that constitutes the electric current in a semiconductor device, in which a semiconductor p-n junction is exposed to the sunlight. Now this photon can be characterized in terms of the two equations. The first equation for a photon is that the speed of light c is equal to lambda v, where this c is the speed of light, and that is equal to 3 into 10 to the power 8 meter per second. This lambda is the wavelength in meters, and this v, it represents the frequency in hertz. And the second important equation to characterize the given a photon is E equals to hv, and that is equal to hc over lambda, where this h is the Planck's constant, and this E, it represents the photon energy. Right? So what we want to achieve from these two equations is to characterize the wavelength of a light which is able to knock out or which is able to relocate an electron present in the filled band into the conduction band. Earlier we have seen that this is in terms of the electron volt, that 1.12 electron volt is required, and because a photovoltaic material is exposed to sunlight, therefore we require to have that type of, or it is easier for us to have that type of you know variable available, according to which we can see the solar spectrum as well. So the solar spectrum is based on the wavelength, not in terms of the electron volt or the band gap energy. And therefore we want to introduce that this lambda into some parameter which can be related, which can we can relate to the band gap diagram of a silicon material. So if I use these two equations, then I come to know that this lambda should be less than hc by E if we want to knock out the electron in a silicon solar cell. So if we plug in the values here, then this lambda should is equal to 1.11 micrometer, or that is equal to 111 nanometer. So what we achieved from this thing, that this equation 1.11 micrometer, or this thing that Eg is equal to 1.12 electron volt, they are actually the same point of interest for us. But if we go with this lambda value, which is the wavelength of a incident light, it would be easier for us to relate the theory with the amount of solar spectrum that we receive inside our planet Earth. So for silicon, any photon with lambda less than 1.11 micrometer shall have enough energy to excite an electron. So this is one important point that we need to understand first. The second important point here is that one photon can only knock out one electron, even if it has an energy which is far more, which is sufficient for two electrons. One photon can only be used to knock out one electron from the filled band into the conduction band, and therefore any energy which is more than the required 1.12 electron volt is wasted as heat. So the band gap establishes the maximum theoretical efficiency for a given solar cell. Because we have started with the silicon only, there are certain other kind of materials which are used in designing a photovoltaic cell, and hence different cells have different efficiencies which are reported either through the calculations inside their laboratory or through experimentation in the real world scenarios. So let us draw a graph here. So graph is available in certain textbooks, and it has on the x-axis it has the wavelength, it has the lambda wavelength in micrometer, and on the y-axis we have the photon energy EV. Somewhere here is, let us say that this somewhere here we have the 1.11 micrometer is the wavelength somewhere here. So if we increase the wavelength, which is obviously increasing on the right side of this particular axis, the electrons which are present, they do not have, the photons do not have enough Eg to excite the electrons. So whatever is the spectrum available here is actually a lost energy. We cannot harness this energy. So this, because this HV is less than the Eg. And this is the same thing that I've written here in the form of a text. And if we start with this 0 point, whole this side is actually a usable energy. But you should remember one point, that one photon can only be able to knock out one electron, and therefore the useful energy is only this much amount of energy. This is the energy which is available here for silicon. I'm talking about the silicon. It is only the usable energy. Whereas if we look into this area, the photons have more than enough energy, and therefore this energy cannot be harnessed and it is wasted as heat. So in a nutshell, the photons with wavelengths above 1.1 micrometer, they do not have sufficient energy to excite an electron, and therefore whatever is available, it is just lost, it is not harnessed. Whereas the photons with shorter wavelength have sufficient energy to knock out the electrons into the conduction band, but any energy above 1.12 electron volt is also wasted, and therefore there is a limited amount of energy, or the efficiency is capped by a number for any given material. So let us see about the solar spectrum that we receive. So we should remember one thing, that the solar spectrum resembles the black body of 5800 Kelvin, and it can be demonstrated that the extraterrestrial reception is 1.1377 kilowatt per meter square. So if this is Earth here, just right at the outside of the surface, we have 1377 kilowatt per meter square is the reception, and then we have the before it reaches to the ground point where we install the photovoltaic panel, it actually encounters the various kind of impurities. We have water vapors, and then we have carbon and whatnot in our polluted environment. So this means that the amount which is reached on the surface of the earth is something less than this 1377 kilowatt per meter square. For all the measurements on earth, 1.5 air mass ratio is taken as standard, and that at 1.5 air mass ratio we have 2% of sunlight is ultraviolet, which is less than 0.4 micrometer. Then we have from 0.4 micrometer to something approximately equal to, less than or equal to 0.8 micrometer. We have the visible range, and then greater than 0.8 micrometer we have the infrared, right? We have the infrared. So for a silicon material, 20.2% energy is lost due to the photons with due to photons with Eg less than 1.12 electron volt, and these are of course those electrons which it is for lambda greater than 1.11 micrometer. Then we have 30.2% is lost due to the photons with band gap energy greater than the requirement of the silicon material. So the rest is this 49.6% is the maximum possible sun energy that can be harnessed using a silicon solar cell. So having said that, we do understand that the choice of a material and the amount of research work in material is the key in designing highly efficient solar photovoltaic module. Some other band gap and cutoff limits are given in the textbook. For example, this gallium arsenide, if this is used as a material for creating a solar PV module, it requires a band gap energy of 1.42 eV. Hence, the wavelength requirement is 0.87 micrometer, which was 1.11 micrometer for the silicon photovoltaics solar panels or solar cells. Thereafter, we also have cadmium tellurium CDTE. It requires 1.5 eV, and hence the amount of light which is able to knock the electrons off should be less than 0.83 micrometer wavelength. And then we have the indium phosphorus INP, which is 1.35 eV with 0.92 micrometer. So the trade-off between the small band gap and large band gap should be discussed now. Now that we have understood these things, we should notice that if we have a material with a smaller band gap energy requirement, then there are more photons capable of exciting the electrons, and therefore more current that device would be able to produce. So the smaller band gap devices means more photons have surplus energy above the threshold needed to create electron hole pair, which accounts for a wastage, and therefore the small band gap devices can provide large amount of current at relatively low value of the voltage. Whereas the high band gap devices, high band gap means they implies that we have fewer photons, because these fewer photons have the enough energy to create the current carrying electrons and holes, and therefore the current is reduced. So the high band gap gives these charges a higher voltage with lesser amount of the energy which is dissipated here. So if you increase this particular Eg here, you have more number of electrons which are available for the conduction band, but at the same time you are having more wastage here, because once an electron is being bombarded by a photon of energy greater than its band gap energy requirement. The rest is all heat dissipation as shown in this purple shade. So the point here is that the choice is not a very trivial choice as far as the efficiency of a given photovoltaic panel or the material is concerned. So once in we see here that for higher band gap we have fewer photons that are required to that are available in the connection band, and therefore the current I is less, the voltage of these higher band gap devices are high. And because the power P is equal to V into I, so there must be some middle ground band gap at which it can give us the maximum possible efficiency. And this is between, for a silicon, it is between 1.2 eV to 1.8 eV. This is between 1.2 eV to 1.8 electron volt for various kind of materials which are present. So the maximum efficiency is in one of the papers, this maximum efficiency is stated as to 20 to 25% for the silicon, which is way less than the amount of or the possible amount of energy that can be harnessed, which is 49.6%. It is because of various reasons. This is not even close to the 49.6%. It is because there are electrons and holes which recombine before they even reach the output. At the output, only 1.2 to 2.3% of the voltage, 1.2 to 2.33 of the voltage is available. And also we have in a given solar cell, something like this one, we have conductors over the cell to collect the charges which are generated because of the photovoltaic effect. The problem here is that some of the photons which are supposedly coming into the, or which are supposed to come into the cell to knock an electron, they are bounced back by these tiny conductors which are placed on top of each cell. Or sometimes they pass through the cell without even encountering an electron, and sometimes they are reflected off the surface of the cell. And then we have the internal resistances available within the cell as well. So therefore the efficiency is between 20 to 25% for silicon, and it is not 49.6%, which was the theoretical value. So having understood with this basic concept of the solar PV cell, in the next lecture we will discuss about the equivalent model and how to electrically model a given cell, and thereafter we will move on to the module and the array level. Thank you very much. Allah Hafiz.